So laboratory project, an elusive limit. So this project deals with a function, and I'm going to write this as f of x. This equals to sine of tan of x minus tan of sine of x. Divide this by, now we're going to look at arc, or inverse sine of x. Yeah, inverse sine of x, this is going to be like this, and then of the inside is going to be arc of the tan. So it's going to be exact same at the top, but then at the bottom. And I'm writing this as arc just because the calculus book has it written like this, and I'll just write it in the inverse form that I prefer in a bit. So this is going to be tan of x like that, minus arc tan. So now it's the exact same as the top, but now you're just doing the arc of it. This is going to be arc sine. Oops, this is going to be r sine of x, like that. And here's moved it in the center, and yeah, let's just write it in the usual format, or the format with the -1 terminology. So the top's going to be the same, sine of tan of x minus tan of sine of x. And then I'll divide this by, now you're going to have the inverse sine of the inverse tan of x. So just write it like that with the power -1 like that. It just means it's the inverse. Now it's going to be inverse tan and then inverse sine inside of x like that. And let's just bold this one just because, or box this out just because I'm used to this one. Alright, so now that we have this equation, so now the questions that we're going to look at are going to be over here. So question 1, use your computer algebra system, CAS, or CAS, just abbreviation, to evaluate f of x for x equals 1, 0.1, 0.01, 0.001, and 0.0001, so 3 zeros. And then the question asks, does it appear that f has a limit as x approaches 0? So solution to question 1. So the calculus book solution manually states it used the Maple Mathematics or CAS software program, which has 10 digits of precision, to calculate the following table of values for f of x. So if you plug in f of x, there's from the calculus book solution manual. Yeah, message me and I'll send it to you. I don't want to put a link out just for legal/copyright issues. Anyways, so if we plug in, so we plug in 1 inside here and then see what we get for f of x. So let's just go over that, then we'll go over question 2 and read it out as we go along. So if we have x is 0.1, then f of x is going to get 1.1838. And then if we get 0.1, we get 0.9281, and then if we get 0.01, we get 2. Again, it's from a solution manual, a calculus book. And we get 0.001, we get 3.333, and then 0.0001, we get 3.3333. So it looks like it's approaching 3.33, or 10 over 3. So the results of this project will vary depending on the CAS and precision level that you're using in your calculator. In this case, it appears that as x approaches 0 from the right side, that's why we have a plus, so it's from the positive side. So it's going to be positive 1, positive 0.1, etc., all the way there. Then f of x is approaching 10 over 3. And note that f is an even function, and I'll prove that in a bit. Thus, f of x approaches 10 over 3. And again, 10 over 3 is just 3.33. As x approaches 0 from the left side, and thus as x approaches 0 from the either or, so left or right. We can show that f is an even function, that is f of -x equals to f of x, so it's the same thing on the left side as the negative or the positive side, as follows. First, let's just recall a bunch of stuff, and this is just for reference. So recall that if you have sine inverse y of x, this is the same thing as writing, this is the idea of the inverse, is the same thing as reversing and writing y equals sine of x. So in other words, inverse is just is a function of the inside variable, and then where the outside is the one that's changing. Yeah, so effectively all it is you're just switching the variables. And then also the tan of y equals x, if you have that, is the same thing as writing y equals to tan of x. So effectively all you're literally doing is reversing these, and also recall that if you were to graph these out, yeah, let's graph this out. So this is going to be the sine and its inverse. Yeah, so if you have just like that, this is going to be your sine function. It goes something like that and keeps going on and on. Let's write this as sine Or actually, we don't need to write that there right now. What we can do now is, I'm just going to put this for reference. So now we can have, let's say we have an x value here, and we have x over there. Then at this point, this is just just to recall for sine. This is going to be our sine of x, like that. But then remember, this is an odd function for sine. So now if we take go with the reverse side of it, so if you go exactly here, which is negative x, the exact same value as this, absolute value, we're going to get exactly this one, which is over here. This is going to be negative sine of x. So it's an odd function. Everything's going to be odd functions, but eventually, when you put them all together, it's going to be even. And now, if we were drawing the inverse, remember the inverse is going to be mirrored across the y equals x line, and in fact looks like this. It's going to look something like this, where it ends up at pi over 2. Yeah, I'm just going to draw it like that. So the inverse goes like that. So again, just recall your inverse function. It looks something like that, where it ends up at over here pi over 2. And yeah, this is all the way to pi over 2. And here, just move that over. This is going to be at pi over 2, like that. And again, the reason is so that we have a one-to-one function. And at this point, it's going to be our pi over 2. For the other side, it's going to be at pi over 2. Anyways, this is for reference. So this graph just goes like this. It doesn't go back in. Otherwise, we're going to have multiple values of y for each x value. Alright, so anyways, now that we have that, so at this x value, we're going to have over here is going to be a negative. It's going to be positive. This is just inverse sine of x. Just to illustrate the difference between inverse sine and sine of x. And then over here, this side is also going to be an odd function. It's going to be negative sine of x. Well, actually, it's written over here. So we'll put those dashed lines for the pi over 2, and put this over here as negative sine of inverse sine of x. So in other words, what we have is, again, just recall that if we have sine of, and this is going to be a negative sine of x, this just equals to negative sine of x, and also inverse sine of x. Inverse sine of negative x equals to negative inverse sine of x, like that. So in other words, these are both odd functions. Odd. And then likewise, we'll show that the inverse tan and tan are the exact same as well. So likewise, if we have, let's just recall the graph of tan. So recall the graph of tan looks something like this. It's going to go like that. This is y. This is x. This is dot, 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 dot. Goes all the way up there. And this is at pi over 2. And yeah, it keeps repeating on the right side as well, but we're just going to ignore that. And yeah, let's say we have a value here. This is going to be our x. So we're going to have a value all the way across here. This is going to be our tan of x. And then the inverse of this is also odd function. It goes down like that. And this is going to go downwards at negative infinity. And we're only looking at from negative pi over 2 to pi over 2. And yeah, this one, let's make this negative pi over 2, like that. Alright, keep going further. So then at this point, if we have negative x, this is going to go all the way down to somewhere across here. Let's make it a bit better, like that. It's going to go all the way across, or make it even a bit nicer, like that. And this is going to be at, this is going to be at negative tan of x. Alright, so now we have this, and then again for reference, let's draw the inverse. Is going to be the mirrors of it, and recall it's going to look like this. So the mirror, so this is the limit going all the way up to pi over 2. The other one's going to go, for the x side, is going to go at pi over 2. So it's going to go something like that. So this is going to go look something like this. Let's try a bit better. Or more horizontal. Let's try one more time. And then it goes like that. And on this side is going to go like that, where this is going to be our pi over 2. So we just flipped the y, x and y. It's going to be a pi over 2. And it's going to go dashed line across like that. And this is going to go dashed line across like that, etc. This is going to be our negative pi over 2. Other one is positive pi over 2. So it goes like that. And at this x value, we're going to have over here, just to show the relative difference, it's going to be inverse tan of x. And then over here, yeah, it's going to be our negative. It's going to be the exact same thing, but mirrored to the negative side. So it's going to be inverse tan of x like that. I mean inverse, yeah, tan of x. Alright, so now that we have this, and this is all just to get that, just to show that again, and it's also for reference for myself, just to get a refresher. So what this also means is that if we have tan of negative x, this is equal to negative tan of x. And if you have inverse tan of negative x, this equals to negative inverse tan of x. But again, this is just for reference, and this is going to mean this is odd. So these are all odd functions. Like that. Let's draw this a bit better. Odd. Odd. Alright, so those are all odd. This is odd. Yeah, because when you put a negative x inside the function, it gets a negative of the same value. But we're going to show that f of negative x equals to f of x, which is even. So thus, yeah, so move over here, just put a line. So it doesn't matter, just put a thus. We're going to show that f of negative x, we're going to plug that inside. So remember, it's going to be sine tan of negative x. We'll put another negative like that, and put another bracket. I'll just put a box bracket just to show the difference. Then minus, that's the reverse, tan of box sine of negative x, like that. Divide this by, now we have the inverse, so sine, yeah, with the negative 1 there, of bracket tan of inverse negative x, bracket, minus tan, inverse tan. Put a big bracket. Box bracket. Now we have the sine. So again, tan, sine, sine, tan. And now we have negative 1. It's going to be negative x, like that. And yeah, the solutions matter didn't go over the proof for why it's even, but yeah, I just wanted to do this for reference and algebra fun. So anyways, now we have this, and we know that a negative tan of x, a tan of negative x equals to negative tan of x. So all these are odd functions. So we could replace all of these tan of negative x and inverse tan of negative x, as well as sine of negative x and inverse sine of negative x with their same equivalent but with negatives. So yes, with their positive equivalent but with a negative. So now we have this equals to sine of negative tan of x, and then minus tan of negative sine of x. Remember, they're all odd functions. And then we have inverse sine of negative inverse tan of x minus inverse tan of negative inverse sine of x. Like that. And now we can do the exact same thing of these ones. So now we have sine of negative tan of x equals to just, well, sine of, yeah, this equals to negative sine. So that the sines also, remember, the sine of this and the tan, we do the exact same thing. Those are all odd functions. So this equals to negative sine of tan of x, of positive tan of x. That's going to be our new x. It's going to be our tan of x. So now plus a negative, and then negative, I'll just put a negative minus, or just put a negative plus. So it's going to be plus tan of sine of x. Divide this by, now we have negative. Yeah, negative inverse sine of positive inverse tan of x, like that. And now minus, this is going to be a plus now. Yeah, plus inverse tan, negative, like that. And yeah, remove this negative now. It's going to be sine, positive. And yeah, so we have this looks like it's opposite, but we can just multiply top and bottom by negative 1. And when we do that, this becomes positive, this becomes negative, this becomes positive. Yeah, so this one becomes positive, this becomes negative. And we get exactly our function. So this equals to sine of tan of x minus tan of sine of x. And this is going to be sine, inverse tan, minus inverse tan, inverse sine. And this equals to our f of x. So thus we have f of negative x. Let's put it like in line with this. So we have f of negative x equals to f of x. So this is even. And we can box this out. Alright, so another way I went over this one, that was just to show that it's even, so the limit, it goes to 0, goes to 10 over 3, or appears to go to 10 over 3 as x approaches 0 from either side, negative or plus, so thus we could just write x approaches 0. And I went over this this bunch of this algebra and math just because this is the one of the only times I'm writing in this video. So now when I do the same calculations using Microsoft Excel, I get the following table of values. So if you have fx equals sine, sine tan minus that, etc. So now if I plug this into this one right here, to Excel, there's a link to it. You can go and download and play around with it. And let's just see what the original one was. We had 1.1838, so that was the benchmark. As long as you get that right, everything else should be. Then you can tell it's calculating somewhat correctly. So we have, if you have x, we plug in this one, we get 1.183831, etc. Then if you plug in 0.1, it gets 1.01, which is different from our earlier calculation, which is 0.9821 from the Maple cast from the solutions menu. So now if you plug in 0.01, we get 1, 0.001, we get 0, 0.001, we get 0. So note that Excel uses 15 digits of precision. And now if we use the Desmos calculator, we get the following. So all the limits are different. So again, we get, if you plug in this Desmos calculator, you could put in fx equals to this. And then there's a link to that one. And then if you plug in f of 1, we get this 1.1838, etc., which is the same as our earlier one. So these two are the same for the Excel. This one's 1.0167. It's also similar. And 3.5. And then, but then if you plug in 0.01, we get 989. Whereas this one rounds to 1. So that just goes to 1. And then the next one's going to be 0.001, we get 0. And then 0.0001, we get undefined. So it looks like it's undefined there. So note that Desmos uses a dynamic system between 15 and 17 digits of precision. So I'm going to write this as proofing at dictionary. So we can summarize below the different calculations methods. So for Maple, that has 10 digits of precision. fx goes to 10 over 3 as x approaches 0. And Excel, 15 digits of precision, we have fx goes to 0 as x approaches 0. And Maple is 15 to 17 digits of precision. Not Maple, Desmos. 15 to 17 digits of precision, and it goes fx goes to undefined as x approaches 0. So we got a bunch of different limits. So thus it is not clear if f has a limit or not as x approaches 0. So now let's look at question 2. Let's just scroll up to question 2. So question 2 states, use the cast to graph f near x equals 0. And the question says, does it appear that f has a limit as x approaches 0? So let's go all the way down over here. And so solution to question 2 is the graph of f near x equals 0 from the solutions manual is shown below. So if we have, this is how it looks like from the solutions manual. It goes to up and down, so it doesn't look like it has a limit or not. And this is 0.01, it's negative 0.01. And so the graph is inconclusive about the limit of f as x approaches 0. Likewise, the graph of f using the Desmos calculator is also unclear, so there's the same link. And this is what we get. So we get some random stuff like this. This is near 0. So yes, it is unclear. And even when you zoom in, it's all unclear. And here's you just go to the browser. So here's the Desmos calculator. So here's the graph. If you zoom in, it just keeps repeating the same thing. So so it is unclear whether a limit exists or not. You get some random values. So now it just doesn't have any values there. Looks like it stopped calculating a while ago. So zoom in, you get some random stuff, and it just jumps up and down. So anyways, that is very interesting stuff. Just keep going further. So now, so it is unclear. So it's also unclear, and that's question 2.